I welcome you all to another session in this practitioner's course on analytics, descriptive, prescriptive, predictive analytics. In the last session, we were talking about machine learning, the intuition behind it, the trips, the traps, the tricks, the intuitive understanding of machine learning. If you recall, we talked about two important traps. One was what if the relationship is non-linear in case you are doing multiple regression, which is one of the most common forms of machine learning methods, one of the most common forms of analytics methods, or if you talk about the toolkit, it is one of the most used tool in the toolkit. Second, we talked about correlation of error terms. Let us now look at some more traps in regression. So, another very important trap or one of the issues which is often ignored, but is very important, is about variance of error terms in regression. Now, this becomes important, this is very common in, for example, stock data. To talk in terms of more layman terms, what this variance means, you know what variance is, right? So, variance is basically a measure of the error, the measure of deviation, the square of the standard deviation is what is variance. Now, often what happens is that the error terms, so for example, if y be your output variable and y cap, this is normally, this is your model output and this be actual output. So, you do a subtraction of these two terms for all the data points on which you want to run your model. Now, this is the error. Now, typically this error should remain constant, but what often happens is that the error is actually not constant. So, this is something called, it's a very it's a tongue twister. This is called heteroscedasticity. So, heteroscedasticity means that your error terms show a variance. The error terms are not correlation. Ideally, when you do a regression, the assumption is that all your error terms, all your errors are same. There is no variation across errors. So, the variation is almost minimal. But in case you have variance in the error terms, this is again an issue, and one of the ways you look at it is through something called residual plot. So, what you do is that, if you recall in the previous slide, we had this errors. So, you plot these errors. So, these are called residuals, which is the difference between what you wanted and what you expected, and these be, for example, the values that you fitted. So, what you see is that though the mean is there, if you, the mean may be following a straight line, but if you say look at the outer quartile range, if you look at the extreme, say for example, the upper quartile and the lower quartile, you see some kind of a funnel shape. Now, this funnel shape basically shows that in reality what is happening is that your errors are increasing. So, over a period of time the previous errors, if you analyze, you will find that the current error is a function of the previous error in a way. So, that is why the errors they expand a lot, and this happens a lot in stock markets, the commodities market, because they are sentiment driven, and when things are sentiment driven, your previous sentiments actually impact your current sentiments, and that is why sometimes the markets crash, or sometimes there is a what they call runs in the market, the bear runs, the bull runs. That is primarily in a way due to this variance in error terms, this heteroscedasticity. Now, how do you deal with this? There are various ways. So, depending on the kind of plot you see, one of the simple ways to deal with it is you do a transformation of variable. This is one of the simplest way. So, for example, earlier you were trying to plot y. Now, this showed a lot of heteroscedasticity. Now, instead of y, you plot log y, or depending on how this shape looks like, you can go by something like root y. So, the whole idea is that these extreme points where the deviation is highest, you tend to reduce them. So, you try to bring more and more reduction as the values inflate. So, this is one of the common ways. Another huge concern, and many a times even these transformations do not work, and that is where you have to look beyond regression based model. The other common issue, a very popular issue, is that of outliers. Now, outliers are simply values which are not in the normal range of values that you would expect. So, for example, you are doing an analysis of some kind of a score, and the scores typically vary between say 30 to 60, but then suddenly you find a score of 90 or you find a score of 120. So, one of the ways is, if you recall in your data analysis, when we do our box plots, you tend to, depending upon the amount of conservativeness you want to have in this range, you try to eliminate the values which are beyond the upper quartile range or the inner quartile range. So, depending on different levels of conservativeness you want, you simply, one of the ways is to eliminate the records. So, for example, if you have some records where the scores are really, so most of the scores are between 30 to 60, but you have one record which is having a 90 value, another record which is having a 120 value. So, one of the simple ways is to simply remove. But this often is not recommended. There are concerns with this, and one of the major concerns is that when you remove, this means you have lesser data to build model, and this means less accurate model. So, in a way, removal is a compromise you do. So, think of this. What was the impact of an outlier? Outlier skewed your model. Presence of outlier made your model less accurate. So, but when you remove the data point, because the number of data points reduce, the model is again less accurate. So, the overall benefit of removing an outlier does not tend to be very high, and often many a times the regressions are done on data sets which are not very huge. When the data sets are not very huge, in that case every data point becomes precious. So, removal is not often, though it may sound the easiest, but it is not the best of the methods. There is a whole domain in analytics, the whole field of study which primarily focuses on outlier analysis and how to deal with outliers. One of the simple ways is instead of doing a removal is instead of removal you cap, and cap means you basically say that anything which is above my upper quartile range, if y be greater than then y is equal to upper quartile limit. So, if y is greater than this limit, you cap it to upper quartile limit. So, in this way you do not lose the data. However, this will work only if you believe that it is a genuine outlier. Many a times the outlier is because you got bad data. It was a printing mistake. It was a data that came from wrong measurement. In those cases, perhaps elimination is the best. So, you have to look into the data, but outlier often, and especially when you are dealing with data in the domain of say survey analysis, a lot of this business related, the marketing related data, where some of the data comes from not from purely automated sources. There are a lot of sources of outliers, the errors that creep in, measurement errors, typo errors. For example, a very classic case is, and this often happens in banks, is that when you apply for a loan, you have to fill a handheld form, and then there is a fellow who then transcribes that whatever you write in your form with pen and paper into machine readable format. So, the transcription at times brings errors. So, those kind of errors you may well better eliminate it. There are other ways of dealing with it. For example, you try to estimate what would be a reasonable way, a reasonable guess, and one of the ways to do this guess is, for example, you build a model on a data without the outlier, then try to estimate what the parameters look like, create a similarity between the data point which had an outlier versus what the rest of the model predicts, and then try to fit in somewhere. There are a lot of ways. It's a complete field in itself, but the point is this outlier is a trap you need to take care of even before you build the model. Now, very closely related to outlier is another trap, another concern, which is high leverage point. So, outlier very high y, the predicted or output value. Now, high is something with very high x. So, in simple case of say a bivariate regression, this means x is a value, for example, if you are plotting your y versus x and this be the typical range, and now you have one value which is sitting somewhere here. So, rest of, say for example, this was the regression line, but this value sitting out here. So, most of the x values are within this range, and this is kind of an outlier. The outlier is typically on the y, but this is an outlier on x, which is called a high leverage point. There is a mathematical reason why it is called a leverage point, but you can intuitively understand that just because of this particular high leverage point, this has the impact this can potentially skew this regression line. So, these values again, just like outliers are traps, high leverage points become trap. It becomes more of a trap when you are dealing with multiple regression. Because in multiple regression, because there are multiple dimensions involved, you may not be able to visualize these high leverage points. Not easy to visualize. Reason being that the value may be within range for each of the different xi's. So, multiple regression means that instead of one x, you have now x1, x2, x3, xn. Now, for each of these x1, x2, x3, xn, the value is within range, but if you look at all of them combined, it is somewhere out of sync. Now, this is one of the reasons why it is very difficult to identify high leverage points, and yet they are the ones that skew your regression big time. They calculate something called a leverage statistic. I'll maybe give the formula, but I will not get into details of it because it becomes too mathy. It is maybe those of you who are interested, they can get into the maths of it, though many softwares will simply calculate it for you. The whole point, however, is to keep in mind that you need to take care of high leverage points, you need to eliminate them, and you need to, before you eliminate them, you have to smartly track them. One final pitfall that we face is collinearity. Now, collinearity means your predictors. By predictors, I mean your x1, x2, if these be the predictors, they are related. So, it means, for example, you are trying to build a regression model on, let us for example take the case of sales. Now, you do a regression of sales for multiple variables. So, from your different sources of data, you have hundreds of variables. So, one of the variable may be advertisement. Then you also have a variable which is radio advertisement, TV advertisement. So, these may be the amount of expenditure made in a year, or the amount of people involved, or whatever. So, most cases expenditure will be the most popular, expenditure will be the most common proxy used for each of these. So, you have radio advertisement, you have TV advertisement, you have advertisement, and then maybe a lot of other things, for example, number of competitors, etc., etc. Now, if you notice these, this may be the, let me be more explicit. So, this is the total advertisement, there is radio advertisement, there is TV advertisement, there may be other forms of advertisement there. Now, you may build a model and each of these variables can come out to be significant. However, if you look, total advertisement is in a way correlated to your TV advertisement and your radio advertisement, which also means that the TV advertisement and radio advertisement can also be correlated, given that the company has a limited budget for advertisement. So, in a sense, there can be multiple variables which are all correlated, or in a sense try to predict the same thing in a different way. So this is a tricky situation, and yeah, one of the simplest way to deal with this is, if you find many of these variables are correlated, first of all the issue is how do you find which of the variables are correlated. In this case, yes, from an intuitive business standpoint you could make a analysis and you can figure out that okay, these variables seem to be correlated. What if you have a huge number of variables, slightly more technical variables, or maybe you are doing an analysis where you do not understand the business very properly? So what do you do? So one of the methods is correlation matrix. So in correlation matrix, what you do is all the variables x1, x2, x3, x4 up to xn xn. So you find out what is the correlation between this. So this may be 0.04, this may be 0.5, this may be 0.7, 0.002. So you create these matrices, this matrix, and then each of those variables where you find high correlation, for example, this seems to be high correlation, this also seems to be reasonably high correlation, and then you try to eliminate these variables. You try to you decide whether you want to use x1 or x3, just one of them, not both x1 and x3, or you use x1 and x or x4 but not both of them. So in a typical case, what you do is you build a model with each of them separately, and then you try to see whether the model works or not. However, let me tell you, because by the very nature of the maths of multiple regression, you may find out that if you eliminate one of these variables, so sometimes this variable also gets eliminated, and what is left is that some of the other variables become important. So just removing one collinear variable can also remove the variable with which it was correlated, and then the rest of the variables become important. So this is why you have to take different variables at a time and then do the same analysis. So one of the ways is to just choose one of these variables. The other approach to deal with this is something called variance inflation factor. I will not get into the maths of it, but it's a metric. It's a metric to determine what is the importance of each variable in itself, ignoring rest of the variables which are there in the model. So typically, if your variance inflation matrix is greater than 5, then it's a concern, or some people they get liberal and they go up to 10. So if your VIF is greater than 5 or VIF is greater than 10, depending upon the kind of problem, that is a variable of concern, and then you try to deal with it. You at least realize, this is the first step, that you realize that yes, there is collinearity there. Now how do you deal with it? One simple method, the easiest and quickest, is drop the variable. And if you ask me, this will work in most of the cases, because you will find that if you remove these variables, because in any case the two variables together were, because they were correlated, there was collinearity, they together were also not able to predict too much of the output. So removing them does not impact too much of your prediction. So one simple way is to simply drop it, the other way is to combine it. So if you recall, in our case we had this total advertisement, we had radio advertisement, we had TV advertisement. So if you combine these together, these are primarily represented by total advertisement. So you can choose to go with this one, and remove these, or you can do a total advertisement minus TV advertisement, which may give a radio advertisement, assuming that it may be the case that radio advertisement itself is responsible for a lot of sales that you get. So, in that case this may be another variable. So, either you combine it or you drop it. These are the two of the most common methods which are used. Okay. So, we talked about regression, we talked about the concept of machine learning, we talked about regression being one of the most important, or one of the maybe the first areas of problem, first domains where machine learning started being used. Apart from regression, there are, so we talked about regression. There are two more areas where machine learning is used. So, this regression, and then there is something called classification. So, regression and classification, they are typically called supervised learning. They are called supervised learning because when you build the models, you have a data set where you know the output. Because you know the output, in a way you are supervising. For each data set you are saying, okay, this was my desired output, this was my model's output, and let me try to tweak the model so that my desired output is as close as to my actual output. So, this is in a way trying to supervise. It is like teaching a child how to speak, and whenever so he says A, B, C, D, and if he makes a mistake, you supervise, you say no, this is how you pronounce A, this is how you pronounce B. So, this is the most common form or intuitive form of learning that we do. This is supervised learning, and then there is another class of model which are called unsupervised learning. Now, this is again, supervised learning is what the way we learn from our teachers, this is the way we self-learn, just by observing, looking into patterns, trying to make sense out of patterns. So, let us look at the next set of methods in machine learning. These are classification methods. We will talk about these in much more detail, but let us have an intuitive grasp of what it is. So, for example, I plot income versus credit card balance, and this is a very common problem in the financial sector. And let me mark by these D's the plots of different people who defaulted, and N be the people who did not default. So, let this be a simple plot. I am just plotting. So, this D means default, N means non-default. So, these credit card companies are often worried about which of the fellows will default and not pay my monthly due, because their profitability operates in a very dangerous zone, I would say, between trying to for most of the companies trying to incentivize the customer to delay the payments, because when you delay the payments you charge interest rate on that, and that is a source of money. But if somebody is delaying too much, that may be because he is not even able to pay. So, it is a very dangerous zone in which they play this game of maximizing the money, and hence this is one of the favorite plots that they always try to make and try to make sense out of it, that who are the people who with different parameters and different variety of parameters who would default and not default. So, I have just taken 2 parameters out there. In reality, there may be hundreds of parameters. So, one of my objectives may be to be able to correctly. So, for example, I have one customer who is somewhere, say, who comes out, say, here. For example, so let me just make it with a different color. So, this is a new case which came. You do not know, this is a new data. So, it's maybe a new customer about whom you do not know whether he will default or not default. You want to now decide or make an estimate of whether he will default or not default. So, how do you go about it? So, intuitively if you look at it, well, it makes sense that roughly it looks as if, you know, this can be clearly partitioned here, and people who are here are mostly defaulters, people who are here are non-defaulters. But then there are some exceptions out there, and then of course, you know, there will always be errors in the model. You do not want to be 100% correct. So, in this case it is simple. What if it was much more jumbled? So, these kind of problems are called classification problems. Now, depending upon whether you can easily separate the boundary or not. So, in this case, because I had to plot, I used only 2 variables. In reality, there may be a large number of variables which are, so there the number of variables can be huge. If you talk of a typical bank which is doing this kind of a default modeling. So, this is often called default modeling, which is just trying to classify people into a 1-0 bracket. 1 means non-defaulter, 0 means defaulters, or vice versa, depending upon the way you build the model. So, the number of parameters, for example, for some of the banks are even 35,000 parameters. So, these may be parameters like demographic, then account history, then credit bureau, the reference with whom he was made a customer, the history of those people. So, and variety. For example, even if you look at account history, that may be the minimum balance he keeps, the average balance he keeps, the number of years he has kept, the number of checks that bounced, the number of times he has met his commitment, number of delayed payments. So, there can be a huge number of variables. It can run into thousands. Now, depending upon the n that you have, depending upon how cleanly separable the data is, depending upon a lot of things, there are different types of methods which are used for classification. In the banking sector, one of the popular ones is logistic regression, and we will talk about it in detail. Then there is k nearest neighbors. There is naive Bayes, which is an extended form of a more generalized LDA model, which are linear discriminant analysis. Then you have QDAs, which are basically instead of linear you have quadratic. Then you have tree based models, decision trees. Then you have support vector machines, and of course these days very popular deep learning, or nothing but neural networks. So this neural networks is a generic set of tools not only used for classification but all forms of analysis. So even for regression and even for unsupervised learning they are used, but their use in classification has seen a lot of uptick trends in the recent times. So this is the classification based models, and then we have unsupervised learning. Now unsupervised learning means see, so far the models that we looked at, there was always a target variable. There was always something good or bad, whether somebody is defaulting or not, whether his height is high or low, or whether his height is 6 feet or 7 feet, whether the sales will be X or X equal to 1 million or 1.5 million. So these are all what we talked about supervised learning. Now we add unsupervised, it means there is no, you are not looking at, there is no target, there is no goal, but you still want to understand the data. So let me give a very intuitive example, and often people fail to understand what unsupervised learning is. But if you look in life, I mean, in fact, unsupervised learning is the most common way that you learn. You take lessons of life, and you try to create patterns out of what you see and observe. Nobody tells you, but that is how we humans are, or the entire animal kingdom is designed to act like. It's all unsupervised learning. The supervised learning is maybe a very small part of what we do. Think of a very simple example. Suppose I have two parameters. For example, let me talk of spend versus earning. So you look at data of people. So just two variables, there can be multiple variables. The people, the amount of money that they are spending every month versus the amount that they earn. And suppose you get suppose this is the kind of data that you look. There are people, who do earn a lot but spend little. There are people who earn little but also spend little. There are people who earn very little but then they spend a lot, maybe many people these days. And there are people who earn a lot, spend a lot. So just by looking at this data intuitively, just on a two-dimensional graph, you can sense out that, okay, this seems to be like one category of people, this seems to be another category of people, probably these are another category of people, these are another category of people, and then these are maybe people in the middle. They are kind of the averages, not getting into any specific category. Or you may want to extend this and include these here and then try to make this as a category. But at least 4 of the categories are very obvious. Now this is the way we look at data and try to understand. This is what we call looking at forest among trees. So just looking at these patterns and trying to find out what the data looks like, bringing out meaning out of it. This is what is unsupervised learning. This is very, very popular in marketing. So in marketing, what they do is when they have to do customer profiling, and this is a very, very powerful tool used there. So for example, if you go into many of these marketing firms, if many of these brand based products, you know, the marketing headquarters of these people, you will find a lot of hoardings of or posters of people, you know. For example, let me just maybe for some fun sake and some more insights into the how machine learning etc. is used in practitioners way. Let me just draw a poster, and you might have seen these posters in many places. So here typically there is an image, there is name of the fellow, there is age, gender is obvious from the image, then there are his profession, and there is some interest statement. There is for example often list of his hobbies, family details. So in a way, kind of an entire biography of a person. So who he is, what is he like, and there can be multiple. So this is one poster, and for the same person there can be n posters. And in many companies, not only posters, they actually have so-called biography of a person. So you have actually those booklets which detail about what kind of books he reads, what is the kind of food that he loves to eat, what does he do when he is free, what kind of colleagues he have, and all sort of details. Now many a times if you visit many shops, in many service centers etc., you will find something similar out there, you know, at least some of these posters out there. So the whole idea, the reason they make, and this is not something, there may be companies who are doing it based on their gut feeling, but actually the way they came out of this was, in many cases, is through what is called cluster analysis. So going back to this slide, so this is nothing but a cluster analysis. They looked into multiple parameters. We looked into just spend and earning. They looked into much more parameters, and they found out what these clusters look like. Now depending upon from a marketing standpoint, depending upon the money, dollar, 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 this may be dollar, dollar, okay, this is maybe this is again dollar, dollar, dollar. So depending upon the money they give, they find out these clusters, they get into a deep dive, they try to get more information about it, as many parameters that support. So in this case we talked about something about collinearity. In this case let us look at the same thing in a different way. In this case, you don't want to eliminate variables which are similar or predict the same thing, because you are not predicting anything. You want all those parameters which are similar. So you may do a unsupervised learning with a small set of parameters, and then you try to add upon parameters which are strongly correlated, and hence you create a kind of I would say a keyword and key parameter list. For each cluster. Try to find out if there is some similarity in these. So depending upon these keyword, these key parameter list for each cluster, they identify which are the customer segments they need to target. And to do that, This is where then their marketing team sits based upon this, creates the image of the fellow. They look at, so for example, once you have these keywords, key parameters, this cluster, they get into different sources and then try to find out which are the actual people who closely meet these kind of parameters. So they create what is called in marketing lingo persona. So this is not an actual person. So you get these key parameter list, etc. Then based upon this, for example, you go online, go into various sources of data and try to find out actual people who look, behave, feel like this, and then based upon all that collective information, you fill in those details. Now the reason they do this is that now this becomes kind of their guiding light for all their marketing strategies. So all their marketing strategies now are based upon these things. So often they would divide the team into separate groups. Each of them is responsible for one particular persona. So often, in many of these very highly brand sensitive products, the marketing managers, they try to live with, they try to kind of feel this persona apart from biography and biodata and etc. God knows, they may also create models and they may create 3D images and holograms and stuff like that. They can do all kind of crazy stuff. I mean, like if you recall that fellow who played that role of Joker in that movie Dark Knight, Batman movie. So he said to have lived as Joker for 6 months, closed in one room, just to live like Joker, read only that stuff and get that Joker inside him, and that is why his performance is rated to be among the most extraordinary performances in film history. Though it's unfortunate that it took him time and it took a great toll on his life, and he died prematurely. But the point I am telling is that they try to live this, and the source of this thing is what is called cluster analysis, and from cluster analysis the entire marketing strategy that flows, right from the way the teams are organized to the way they target their customers, the kind of product propositions they give, the kind of marketing offers, the kind of sales incentives they give, that is often in many state-of-the-art marketing organizations is driven through this persona-based marketing analysis, the persona-based customer analysis, which is nothing but clustering or unsupervised learning. Apart from clustering, another unsupervised learning which you may have done if you have done course on marketing research is PCA, or nothing but principal component analysis. Now principal component analysis, again, for those of you who are comfortable with matrix algebra, who have done a course on linear algebra, they can get into the maths part of it. Let me just give you a very high level intuition about what it is, what we are trying to do. So what we are trying to do basically is that from a practitioner's perspective is that we have, for example, as I said, in many cases 35,000 variables. Now these so many high number of variables are again a nightmare to deal with. How do you deal with so many variables? And then there is a whole sort of collinearities there, and more variable doesn't mean always more information. More often than not, it means more noise. So principal component analysis is try to see whether we can summarize some of these variables and then have one variable represent these. So in a way, what we are trying to do with principal component analysis is that say x1, x2, xn are your variables. So can there be, say for example, I choose x3, 3 of them variables. Is there a way I can make a 1 to k, can I make a linear combination of these variables? That linear combination, which is, okay, let me try to, so which is nothing but a1 x1 plus a2 x2 plus a3 x3, for example, if it is a, if there are 3 variables. So can I maybe write this expression and then remove these 3 variables? So in a way, what I am trying to do is to reduce my number of variables. Now I lose some accuracy in that. So what principal component analysis does is that it gives you those linear combination of variable along with a metric of how important is this, what is the kind of loss of information that you have if you combine these variables. So instead of having ax1, x2, x3, if you have all these 3 combined, obviously, so this linear, because life is not linear, so there is some loss of information that happens. So we will talk about this when we discuss it in slightly detail, but the concept is that can this linear combination replace these x1, x2, x3, and if it can replace, then let me try to reduce my number of variables. So the whole idea is to reduce number of variables. So I am not doing any regression, etc. All I am trying to do is trying to find out which of the variables can be combined, and in a way it's again looking at patterns. So for example, and often, by the way, this principal component analysis is again, we talked about this cluster analysis, we talked about this persona. This principal component analysis again used in persona. So for example, in case the 3 variables that you found useful were like age, then marital status and income. So, well, you can say that if somebody has a matured age, is married and has high income, he is probably somebody mature or high social status. So you may say that these 3 variables kind of represent social status, not very accurately. Maybe if apart from income, you also have a variable called designation. So you find he has a very high designation. So you may say that, well, these 3 variables, I combine them together and I create a new variable called social status. So this is again very intuitive, it is easy to understand and feel. So from a marketing perspective, from a decision making perspective, it gives you a way to get hold of, get a business sense, get an intuitive sense of what these things are talking. So often what they do is, from an operational standpoint, they try to create these principal components, and based on this principal component, they try to see if I can give some kind of a business meaning to this. So if you can give a business meaning to it from a practitioner standpoint, from a management standpoint, that means a lot of my marketing, lot of my strategy, lot of my financing, a lot of other things I do in the organization to increase my shareholder value, that can directly flow from there. So primarily principal component analysis and cluster analysis, they form part of what is called unsupervised learning. So we looked into classification, cluster analysis. We have already looked into regression based analysis, which covers primarily the most of the way machine learning is being used in industry. Practitioners use it. In the next class, we will talk about another emerging field. It's not emerging, but it's becoming very popular even in a business domain, which is the reinforcement learning based machine learning tools. We will look about that, and then we will also look about some more aspects of doing good machine learning based analysis. Thank you very much.